I'll be talking today about data materialization, which is a super important topic in any kind of analytical system design. And so I'll be talking about how I think about it and how I think what I think are good ways to think about it, and also what tools you can use in various systems to implement what you decided is the right way to do materialization for your project. And then I will be also highlighting some new tools that we have shipped in Apache Druid recently in this area. First off, data materialization is the act of storing a copy of data. And I say copy, but you always have at least one copy. So you're always materializing something. A materialized view in a database is an optional feature, but there's always the base table in a database. There's always files at S3. There's always topics in Kafka. To me, each of these counts as a kind of materialization. So you're always materializing something. This is the picture that shows how I think about things. There's something happening in the real world. You don't have a digital copy of that. It's real. So it's actually happening. The real world has not yet been digitized. We don't yet live in the matrix. You ingest information about what's happened in the real world, and that ingestion process leads to queryable data. Queryable data can then be queried by a query engine, and the query engine is triggered by the end user, and the end user is triggering that query engine through either a user interface or an API. So some examples of what might be the queryable data that you're materializing. A really common approach is to use a DBMS, a database management system. So it could be a relational database, it could be a non-relational database like Elasticsearch or MongoDB, some kind of database management system. And typically in a database management system, you are going to have the queryable data and the query engine combined together in a single system. So it's storing a copy of the data and it has a built-in query engine. So you imagine storing a copy of your data in Postgres and using Postgres's SQL language to query it. Another really common approach is to store your data in a data lake, such as Iceberg or Delta Lake, and query it with something like Trino or Spark. And something that's a bit more of a new approach is to have your queryable data stored as state in the stream processor. So Apache Flink has this feature where you can query state, and so you can have a Flink job reading data, updating a local state store, typically a key value store. I think it can be anything. And then you can query that state directly. So these are all ways to have some copy of data that is queryable and some engine to query it. That engine may be tightly coupled with the data, or it may be decoupled. So when you're designing a data system, when you're designing a analytical project, you have to decide where to draw the materialization line. Where is the line between the real world and what the query engine sees as its queryable data? The simplest thing to do is the natural form of the data. So we'll start there. That's raw records in whatever form they're generated at the source. And the source is whatever is getting data from the real world. A lot of times these are key value objects like JSON objects. They can be in some other format that's equivalent to JSON. They can be text. They can even be images or videos. They're going to be some kind of raw information. Database systems make this easy when they don't require schemas or when they have features like variant columns and JSON columns. Not all databases have those features, although many do these days. They're common features that make it easier to store data in its most natural form. It is important to watch out for performance implications when using these features. Some databases implement JSON columns or variant columns in ways that don't have a performance hit. Some implement schemaless storage in ways that don't have a performance hit. But some do have a performance hit. Some will say that they're faster if you define types. So you want to watch out for that kind of thing. A little plug for Apache Druid. In Apache Druid, we have an implementation of schemaless ingest and JSON columns that does not have a performance hit, which we're very careful to do it that way. With this simplest approach of storing the natural form of data, you get flexible query patterns. You can, in theory, answer any question of the data because you're storing it at full fidelity. The downside is that this approach has the highest storage footprint and the worst query performance of any approach. The query performance tends to scale with the storage footprint. Although performance can still be good, do not assume that storing data in its natural raw form is a bad idea. Modern data systems are extraordinarily capable and extraordinarily fast. And many modern data systems that you heard about even at this conference are capable of querying raw data in its natural form at a performance that you're going to find acceptable. So don't assume this is going to not perform well. It just will not perform as well as potentially other options. The other extreme, that's one extreme, is storing in natural form. The other extreme is to store exactly what you want to visualize. This was a common approach in the early days of real-time UIs. It's, I would say, less common today, but I still see people do it sometimes. A typical pattern here is to use a stream processor to incrementally update stored state in a key value store. The idea here is that your UI or your API is going to be, it's going to want to draw, for example, a table on the screen or a time series chart or a bar chart, and the data points it's going to put in that chart are those literal data points are being stored in your database. For a UI with few controls, so imagine perhaps a dashboard with no controls at all. It's a real-time dashboard, but there's nothing you can click on. Or imagine a real-time dashboard where there's limited controls, such as you can change the time range, maybe filter on one or two things, but that's it. For those scenarios, you've got a very low storage cost, very high performance. Although as the UI gets more flexible, the storage cost blows up exponentially because you start needing to compute every possible screen that can get drawn. And as the UI gets more flexible, the number of possible screens does blow up exponentially. So this is something that is a relatively extreme choice. Like I said, I think it's with data systems getting much better and much faster and much more efficient, this is less common than it used to be. Although I still wanted to call it out as one of the two extremes of what you can do. Another thing you can do is there's this concept in analytics of events and entities. So events are immutable objects, things that happened, and entities are mutable objects. They're things that are being described by their current state or by their state at a particular point in time. So if you have an immutable event stream that represents changes to entities, you can materialize those entities. A common approach here is to materialize the latest or the current state of each entity. So one example is your events might be page views, and you want to construct entities out of those page views corresponding to user sessions. So each page view is an immutable fact, something that happened, whereas the session is something that evolves over time. The session length is changing over time, the number of pages visited is changing over time, et cetera, et cetera. If what you want to query is the entities, then materializing the entities in your database can be helpful because it means you don't have to then compute those entities at query time. And computing the entities from the events at query time can be expensive at query time. It can involve expensive subqueries. Another really common approach is to materialize filtered or partially aggregated datasets. Many databases support doing this as a built-in feature, which I'll talk a bit more about later. One example is materializing hourly sums across various dimensions. So if you ever want to do a query that's like group by XY, sum Z, materializing the sums of Z's for every possible XY over each hour can reduce the dataset size by partially aggregating it. For example, you could materialize a list of anomalous findings that require action, so you don't have to search for them every time you query. In other examples, you could materialize the data set corresponding to a specific whale user. Many multi-tenant systems have this property where the biggest user is many times bigger than the next biggest user. You have these whales, and so the data associated with these whale users can be much larger than the data associated with any other user, maybe the next many users combined. And so you may want to materialize a data set that's just that user's data. To speed up queries that are being driven by analyzing the usage of that user. Another thing is you can have multiple materializations. You can have as many as you want. There's nothing stopping you from doing that. The main trade-off to think about is storage versus query time compute. Every materialization you add requires more storage. And if you have materializations, the point of materialization is to minimize query time compute. That's why you have multiple. So as you add more, you are saving query time compute, but you're spending on storage. In general, that's a good thing to do because compute is typically more expensive than storage. And so that's why having multiple materializations is such a powerful concept. I would say like a typical number of materializations in an analytics design that I've seen is 1 to 4 or 5. So it is typical to have a few. Also consider ingest time compute and cache usage as trade-offs. The main one is storage and query time compute, but these two are also important to think about. Materializations do require compute to produce, and you need to think about that. They're not free in terms of ingest time compute. And also, if you have a lot of specific materializations, that can mean less cache space available for the base data if the base data and the materialized data are all being queried by the same query engine. They're all leveraging that query engine's cache. And so they can contend with each other for cache space. So I next want to talk about, after talking about why you might want to do materializations and what to think about when deciding you want to do one, now I want to talk about how you can do materializations. So the first approach I want to talk about is external materializations. This is the most flexible and generic approach. You're using stream or batch processing outside the system that you're using to store the data. So in my way of thinking, it's part of the ingest process. So as part of ingesting, you're creating multiple materializations of the data. This is very flexible, although it has a problem, which is that it's difficult to keep materializations in sync. Imagine you have a database and you have a table that's the base table, then you have another table that's partially aggregated, aggregated to the hour. It's very difficult with an external materialization approach to keep the base table and the materialized to the hour table in sync. One thing you can do is you decide you don't care. It's fine if they drift a little bit. If you do want them to be in sync, you would need to use transactions in the database to keep them in sync for incremental updates. Although then if you need to do an update that updates more than just an incremental change, then you end up doing a really big transaction, which could cause problems with the transaction system in the database. It can cause problems with read-write contention. So it is difficult to keep things in sync. And also with query time, you need to explicitly choose which materializations to use, which can be annoying for your users that are writing queries. So this is a flexible approach. This is using something like Spark or Flink to create a separate copy of the data. It's a very flexible approach, although typically if the next approach is possible, people would tend to prefer it, internal materialization in the database. So many databases support materialization internally, multiple materializations internally. These features tend to have names like materialized views, projections, dynamic tables, and even indexes can be thought of as a materialization. One word of advice: do not get too attached to the names of these features. They do mean different things in different databases. For example, in some databases, a materialized view can automatically substitute for the main table, but in some databases, it can't. The latency of updating can be very different from database to database for these different named features. So do not really think too much about what the name is. Don't assume that a materialized view in one database is the same as a materialized view in another database. They do tend to behave differently across systems. Instead, think about more fine-grained effects you can see and the things that you have to pay for. So one very important one is, can a materialization automatically stand in for the main table? So imagine you have a materialization that is partially aggregated or partially filtered. If a user writes a query on the base table with a filter or an aggregation that matches the materialization, will the database system automatically substitute the materialization for the base table? That's a very helpful feature and one you should be considering whether you get that feature. Another is, what is the update latency? So with some systems, we can guarantee that a materialization and the base table update at the same time, and sometimes it's not guaranteed. So is there an update latency? Another question is, how is the materialized view or projection or dynamic table, how is it updated, and what is the update cost? For a cloud service, the cost is going to be measured in dollars. You want to ask how much I pay in dollars to update it. And for an open source system that you're running yourself, the update cost is going to be in compute. So you want to know how much compute it's going to take. Is it something that needs to be recomputed from scratch on some cadence, which is an expensive operation? Is it always incremental? You want to understand how that's going to work. Another question that's important is what happens if materialization cannot be updated incrementally? Incremental updates are the best way to update internal materializations because they minimize the compute cost of updating materialization. Although it's not always possible to fully update a materialization incrementally. One example is if the materialization and the base table are clustered differently. If they have different clustering, then we may need to recluster the materialization, which requires a recomputation of it. Another example is if a materialization is defined after the base table has already been populated. And if that's the case, then there's a question about, okay, well, how does the initial population of the materialized view happen? So these are all important questions to think about. And the one takeaway I hope you have from this slide is, and maybe even from this entire talk, is that you want to think about these kinds of things rather than just looking at the names of the features and assuming that a materialized view or a projection behaves the way you think it behaves, no matter what system you're using. So now I want to talk a bit about how internal materialization can be implemented in various systems. So the two main categories of implementations, and by the way, this applies whether we're talking about materialized views or projections or dynamic tables, no matter what we're talking about, these two broad categories still apply. The first broad category of implementation is what I would call a hidden table. And a hidden table is internally in the database, it's implemented like a regular table. It's just not a table you can query directly. So what that means when I say it's like a regular table, typically it has its own storage that's separate from the storage of the base table. And so when you're updating the base table, the hidden table gets updated separately, either through a trigger or through a background job. Hidden tables can be refreshed periodically. So the database would support an operation to do a full refresh of the hidden table by essentially clearing it out and then recomputing it from the base table. Many database systems also support updating these hidden tables incrementally, as I mentioned, typically through triggers or something like it, something that behaves much like a trigger. I.e., when you insert into the base table, a trigger would fire that does a insert into the hidden table that's appropriate for the materialized view. This does require databases to restrict what you can do with these materializations. You cannot allow any arbitrary query operation to run if you want to update things incrementally, because not every query can be incrementally updated in terms of its results. So database systems typically have some restrictions on what can be put into a materialization that is incrementally updated. Typical restrictions include being restricted to operations like filtering and aggregation. Another approach, another category of approaches, is to embed the materialization within the base table, as opposed to having a separate hidden table. This is common in systems that use immutable parts under the hood. So it's very common in OLAP systems. OLAP systems tend to be columnar, and they tend to use immutable parts to storage. So when you add things, when you do an insert into a table in an OLAP system, what tends to happen is those inserts are batched, and an immutable file is created in columnar format with each batch of inserts. And so there's a natural way to embed materializations with the base table. You can embed the the incremental update in that same batched file with the original base inserts. So this is a common implementation in OLAP systems. One limitation here is that it must have the same clustering as the base table, because they are literally embedded together with the base table parts. So they cannot have different clustering than the base table. But incremental updates are always happening. And another nice thing about this is that it's guaranteed that the materialization and the base table are in sync, because we are literally adding the materialized incremental update and the base table update at the same time in the same batch file. Most systems that support these embedded materializations also support using some parts that have a materialization and some parts that don't for that situation where you create a materialization after the initial table is already populated. So what I mean by that is, let's say you have a table, you insert a billion rows into it, and then after that you create a materialization that's partially aggregated to the hour. What most systems do that support embedded materializations will then apply that materialization to future parts that are ingested. And then the prior parts, you may either issue a manual optimize command to update those, or it may happen as part of an automatic compaction or vacuuming process. So I think the takeaway that I would hope you have from this slide is, think less about the names of the features, think more about how they're implemented. Think about, are they implemented as hidden tables? Are they implemented as embedded within the base table? And are incremental updates possible? And if so, how do they work? I also want to talk about indexes. Indexes are a very commonly used feature in databases, and they can actually be thought of as a kind of embedded materialization. They are updated along with the base table, just like embedded materializations. Their typical use is to speed up where filters, but in some database systems, they can also answer an entire query. For example, in Postgres, there's a feature called index-only scans, where if you have a index on X and Y in a table, and then you do this query where you select X from the table, where X equals key and Y is less than 42, Postgres will actually do that query only using the index, not using the base table, not using the data section of the table. And in that case, the index is acting like an embedded materialization. So as you're thinking about ways to materialize your data, different ways to materialize your data in order to optimize your queries, expand your mind to also think about indexes, because in fact, indexes and materializations are two sides of the same coin. They really serve a lot of the same purposes, and in some databases, they can achieve the same things. I want to close out by talking about our approach to doing this in Apache Druid. As you mentioned, I'm a member of the Apache Druid project. That's where I spend most of my time. And we've recently shipped a feature called projections. That is one of the names that this feature has in various databases, and this is the one we use for our feature. That is a materialization feature. It's experimental in Druid 31, and it's designed to support partial aggregations, and they are embedded. Druid is an OLAP system, and so we did this common approach in OLAP systems where we embed within the base table, and they're incrementally updated. So the way that they work at query time in our implementation is we actually push the choice of which projection to use down to the data server, which in Druid are called historical nodes. So query comes in on each individual data server. Each file, each segment file, which is a segment file is a file on disk that is in columnar format and has typically a few million rows in it. So a typical data server is going to have thousands or hundreds of thousands of these files. Within each file, we have the base data, and then we have some embedded projections of the base data. And on a file-by-file basis, the system will decide whether to use the base table or whether to use the projection. And this is what enables the system to intelligently mix some files we're going to use the base table, some of the files we're going to use the projection, which is something that makes a lot of sense for projections that are added after a table is already populated. Not all the files will have all the projections. This stands in contrast to making the decision at the SQL planner. We don't decide at the SQL planner because if we decided at the SQL planner to use a projection or not, then we'd have a problem if we got to a data server and one of the files didn't have that projection available. This is a illustration of what a projection might look like inside one of the segment files. So the base data is on the top here. We have the base data has columns like time, category, product, unit price. This is a sales data set. And then we have a single projection here, so a second copy of the data that is a partial aggregation by category. And so you see that there's two categories here, produce and beverages, and then we have an aggregation across the entire segment. So if a user did a query where they wanted to sum the prices by category equals beverages, then we're able to use this projection. And we only have to read one row per file as opposed to many rows per file. So the query time compute is much, much less because we're just reading one row per file instead of however many there's going to be. We did some benchmarks of this. Benchmarks of these kinds of features are a little bit silly because you can make them say whatever you want. Because that's the whole point of materializations, is you can draw that line wherever you want. So the only purpose of this is just to show that what kinds of things are possible in a typical scenario. So in a typical scenario, you can expect to see quite a lot of speed up with materializations and partial aggregations in cases where they're actually able to be used. Thank you so much. I hope that you enjoyed this talk about materialization and about how we approached it in the recently shipped projection feature in Apache Druid.